So starting off with calculus, I'm going to change my equation to x to the negative 2. Then the derivative is just the power rule, negative 2, x to the negative 3. Just for figuring things out, I might take the time to write it like this. Now, if you try to make that equal to 0, because we're looking for where, we're looking for points where the horizontal is 0, because that's when we're going to have a maximum or a minimum. If I try to do that in this case, there's no solution. Okay? Partially, you can see that there's no solution is if I wanted to get rid of the fraction, I could multiply both sides by x cubed. And then since everybody knows 0 is equal to negative 2, you just keep working from there. And, run into a bit of a problem. Yeah. I'll show you, see if you can, later I'll show you a proof right after this one. Remind me of why 0 is equal to 1. And then you can see if you can figure out why that is. I've showed you that one before? Maybe? Okay. 0 equals 1. We'll see if I've shown it to you before. I'll put it up after. Anyway, 0 equals negative 2. That would also say something's wrong here. There's no solution. That doesn't mean that this one doesn't have any critical points. Because critical points were where the derivative equaled 0, and in this case that has none, but also wherever you have non-permissible values. Can you see from our original equation that we have a non-permissible value? What can't x be? X can't be 0. So when we go to our chart, we can put 0 on there as a place to check, because at a non-permissible value, a function could change from increasing to decreasing as well. It might stay the same, but we're going to find out. So from this, what we're going to do now is we're going to look at our derivative. We're going to plug in a number less than 0, a negative number. A negative number cubed would still be negative, and so you'd have negative 2 divided by a negative number, which will give you a positive number. So we know our function is increasing before 0. After 0, when we plug in a positive number, you're going to have negative 2 divided by a positive number will give you a negative number, so we know that it's decreasing after that. So because we know we have a non-permissible value at 0, we can draw that asymptote in at x equals 0. From our calculus at the beginning of the year as well, if we think about what happens as x gets really, really big, the limit as x goes to infinity of 1 over x squared, it's going to get really, really close to 0. So there will also be an asymptote at y equals 0. Another observation that you may make from this one, this function will always be positive, because squaring on the bottom makes it positive, and you have a positive 1 divided by a positive number will always be positive. How can I show that it's increasing to 0? Well, my graph would look like that. How can I show that it's decreasing after that? It would look like that. Now, reminder, how did we do these ones using stuff from grade 11 and grade 12? We knew these points, minus 1, 1, and 1, 1. Okay? Do you remember graphing x squared first? And then on a reciprocal graph, which when you, this is y equals x squared. So if I wanted to graph y equals 1 over x squared. Wherever it's 0, there was an asymptote. We learned that if it kept getting bigger and bigger, 1 over that would keep getting smaller and smaller. So there was an asymptote at y equals 0 as well. And then we took any value that we had on our original graph. For example, 1, 1, that point will stay the same because if you do the reciprocal of the y value. If I took another point, say 2, 4, all the reciprocal does is change that to 2, 1 over 4, and then you learn just to draw it to the asymptotes afterwards. The calculus helps explain why it's increasing here and decreasing afterwards. So see if you can use calculus for the next one.